Hello everyone. I'm going to talk about a very simple system which could be used to generate clean, affordable, and reliable electricity. The system harnesses excess buoyancy of an object as it rises from the bottom of a water body such as a dam, large water tanks, or even the ocean to drive a generator. In the video, we have an object pulling a rope as it rises. A gearbox converts the linear motion of the object into rotary motion, which is transmitted through a shaft to a transfer gearbox which drives the generator. Here we have two objects running alternately to ensure continuous rotation of the generator. When the object reaches the top and starts to sink, the drive gearbox will allow the rope to recoil, getting it ready for the next pull cycle. This image shows the main components of the system. Let's look at how an object rises and/or sinks in water. You would recall the concept of buoyancy and Archimedes' theorem from middle school physics. Just to refresh your memory, basically, if an object's density is less than that of water, it will float. If it's more, it will sink. Example, object A has an external volume of 1 cubic meter and weighs 500 kilograms. Its density is less than that of water, which is approximately 1000 kilograms per cubic meter, so it has a positive buoyancy force of 500 kilograms. Object B has the same density as that of water, so it is neutrally buoyant. Object C has a negative buoyancy force of 500 kilograms, so it would sink. Now, let's take a closer look at how we get the object in our system, herein referred to as the buoyancy tank, to sink and rise. I'll use some arbitrary specifications, however, the system is scalable. Our tank has an external volume of 1 cubic meter, its weight including a few components inside the tank is 400 kilograms. I will talk about the components inside the tank a little later. This tank has a positive buoyancy force of 600 kilograms. If it was anchored at the bottom of a water body, once released it would rise. If the same tank was allowed to take 800 liters of water, image B, the new weight would be 1,200 kilograms, so the tank would sink. Now, let's look at how we get water into the tank so that it sinks and out so that it rises. This image shows the tank and the components inside the tank. This one shows how the components are arranged inside the tank. Getting water into the tank. While at that level in the water body, the tank just needs an opening or valve at the bottom and an open vent hose, and the water will simply fill up the tank while pushing the air out. Please note that there would be a locking mechanism to lock the tank to the guide rails while filling it up, or pushing the water out. Once the tank is filled up, the valve will close, the lock will release, and the tank will sink. Pushing the water out. Once the tank reaches the bottom, the winch, not mentioned in the components list, will release the small weight to compress the water in the tank, thereby increasing the pressure since water is incompressible. This pressure will be transmitted undiminished, evenly throughout the fluid, Pascal's law. The formula pressure equals force over area is used to determine how much the pressure increases by as a result of the weight. Given an opening with a diameter of 10 cm, 0.1 meter, on the piston, a 23 kg weight will increase the water pressure in the tank by 28.9 kilopascals, resulting in the pressure in the tank matching the hydrostatic pressure in the water body at a depth of 3 meters. Next, the winch will release the big weight to sit on top of the piston. A weight of 200 kilograms on top of a piston 1 meter in diameter will result in the pressure in the tank increasing further by 2.5 kilopascals, so it's above that in the water body, so the water in the tank will be pushed out due to the pressure difference. Please note that an air vent would have to be open to allow air into the tank as the water is being pushed out. This image shows the tank after the water has been pushed out. At this stage, the winch will pull the weights and the piston up to the top. Again, both air vents would have to be open to allow air above the piston out and air into the tank. As mentioned earlier, there will be locks on the guide rails to lock the tank while water is being allowed into the tank or being pushed out. The locks will then release to allow the tank to rise or sink. Potential energy input and output. Based on the tank specifications used in this presentation, here are some energy input and output estimates. Input. Opening and closing the valve at the bottom of the tank, negligible. Opening and closing air vents, negligible. Lifting the weights and piston up after pushing the water out, 250 kilograms up over 1 meter. Work done is 2,450 Newton meters, 2,450 joules. Please note, I have not taken into account the energy required to overcome piston friction. This is because a retractable piston design is being considered. It allows the piston to shrink very slightly after the water has been pushed out. This would reduce the effort required to lift the piston significantly. Output: a 1 cubic meter tank weighing 400 kilograms, after the water has been pushed out, will have a buoyancy force of 600 kilograms. If the tank rises over 3 meters, the work done would be 17,640 Newton meters, joules. Assuming that the tank completed one cycle in 12 seconds, this could potentially be a 1 kilowatt system, taking into account the energy input per cycle. If 6 tanks were used to drive one generator, then the system would be a 6 kilowatt system. As mentioned earlier, the system is scalable, so if several much larger tanks were used, the size of the water body available permitting the system could potentially generate hundreds or even thousands of kilowatts of energy. I didn't go into the finer detail or specifics of the concept so as to make this presentation as short as possible. However, for further detail, clarification, comments, suggestions, or to partner with us, please feel free to contact us via email at uniquahydro2@gmail.com.